Hello and welcome to the Omnex webinar, SOTIF Mission Accomplished, the new international standard ISO 21448. The presenter for today's webinar is Dr. Juan Pimentel. Juan is an Omnex consultant with extensive engineering, safety, and cybersecurity experience. Prior to joining Omnex, he was a professor of electrical and computer engineering at Kettering University. Juan has an interest and continued to be involved in standards and having served on standards liaison in the Industrial Electronics Society and the IEEE Standards Board. He has participated and continues to participate in various standards, including the SAE Vehicle Electrical Hardware Security Task Force and the SAE ISO 21434 Automotive Cybersecurity Task Force, and the ISO PAS 21448 Standard Task Force. During this webinar, if you have any questions for Juan, please enter them in the Q&A box, and he will get to them to the best of his ability at the end of the webinar. The webinar is being recorded, and someone from Omnex will reach out to you within a week or two with how to access the recording. All right, Juan, you can take it away.
Okay, thank you very much, Miles. Let me share my screen real quick and get started. All right, Miles, do you see just one screen?
I am not seeing your screen. You need to click the green share screen box that's in the.
How about now? Do you see my screen now?
It says you've started sharing, but I don't see the screen just yet. There we go. You have to go to presentation mode. Still though.
You still don't see it?
I just see the PowerPoint. It's not in presentation.
Yeah, the PowerPoint presentation. Do you see that? Yeah.
I'm seeing the wrong. Yeah, there you go. Switch that.
All right. Do you see just one screen or two?
Yes, it's correct now.
All right. Yeah, good morning. My name is Juan Pimentel, and I am pleased to offer you this seminar on a new standard that was just approved in May of this year, which is ISO 21448. You have probably seen some of these slides, which is an introduction to Omnex, okay? So I'm not going to spend too much time about this. You will get a copy of the printed copy of this presentation that will include some of this information. All right. As you could see here, Omnex actually targets several markets: automotive, aerospace, semiconductor, electric and autonomous vehicles, medical devices, and manufacturing. This webinar targets automotive. A little bit about myself, as well, it was mentioned before. I have an extensive background in functional safety as well as automotive. I used to be a professor at Kettering University in Flint, Michigan, and now I'm a international consultant. This is the abstract of the webinar. Basically, what we're saying here is that NHTSA has published information about accidents, and it turns out that only less than 1% of vehicle crashes are attributed to vehicle failures themselves. The rest are related to other reasons, including driver drivers, whether or not they're automated or manual. So this standard 21448 then is very important because it promises to address the issue of these accidents. So this is the contents. I will provide a brief introduction to some terminology, such as ADS, HAD, and ADAS. I will review very briefly the SAE automation levels, which is very important. And then I will move to the fundamentals of SOTIF, emphasizing the 4 areas, areas 1, 2, 3, and 4. And then, of course, I will cover an overview, the SOTIF standard, and then emphasize the main clauses and the annexes. At the end, I will provide an integrated implementation with SOTIF and functional safety, as well as an example, including a adaptive cruise control. All right, so there are some terminology that's related to autonomous driving, and there are basically 3: ADS, ADAS, and CAD. So ADS, it's the umbrella type of term that includes automation levels covering 1, 2, 3, 4, and 5 of the SAE International Automation Level Standard. Now, as a subset of that, we have 2: HAD, which is high-level autonomous driving. As you could see, it covers 3, 4, and 5. And ADAS that covers 1 and 2, the levels 1 and 2. So you could view ADS as being ADAS plus HAD. That's one view. However, I must mention that some definitions actually say that ADS is equivalent to HAD. However, ADAS is fairly well established, strictly 1 and 2. So you may find some definitions that are slightly different than this one. But nevertheless, in my opinion, the most important things is whatever definition you use is to find out what levels does it cover. Here are a few examples of ADS systems at levels 3 and 4 in this case. So examples get different names. For instance, traffic jam chauffeur systems, and mostly European terminology. In the US, it's traffic jam pilot. And likewise for the next one, motorway chauffeur system or highway pilot, urban chauffeur system or urban pilot, and automated valet parking systems, also called car park pilot. So as you could see, these are automated systems for a variety of uses. For instance, traffic jam, traveling on the highway, in a city, or in a parking lot. Just as a brief background, here we're showing a lot of stuff primarily related to sensors and controllers in the car, as well as communication systems. So we're particularly concerned about environmental perception sensors because those are very critical for SOTIF. And as you could see here on the right side, you have parking sensors, you have radars, you have cameras of various types, and you can also see in this diagram some controllers, which are the ECU portion. So the ECUs are controllers, and then we have some other type of information, which is called perception sensors. In yellow, we also have some motion actuators, and in green, we have the actual controllers. So this is to illustrate the type of elements, if you will, or hardware and software in a car that is directly related to ADAS and the automated systems. Also, the standard uses a model called the Sense Plan Act model. And the idea is that the first thing that happens is that you sense the environment, okay, through sensors, obviously. Once you have a pretty good idea about the environment, then you go into what is called planning and control. So this middle portion has to do with control functions, and planning functions. Once you have that, then on the right side, you have the actuators. So this is where the controls get actually implemented in the car and make the car move in certain ways. Other terminology that really comes from the SAE side is the DDT, or dynamic driving task, which is, you could think of it as really all of the activities or actions that needs to happen in order to operate a vehicle. So if you as a driver, for instance, whether or not you realize it or not, but you actually do all of these things, okay? The main difference in automation is that we're going to have a robot, a computer, sometimes called robot, to perform these functions, either totally separate from the driver or in conjunction with the driver. So the main functions, as you could see, is lateral motion, which means steering, longitudinal, which means braking or acceleration. However, there are other activities, as you could see, like monitoring the environment. Another one is to detect and also respond to objects and other events in the environment. Still another one will be enhancing conspicuity via lighting, signaling, or gesturing. In other words, you're changing the environment. Another terminology that's used very much, very important, is called ODD, Operational Design Domain. And what that means is that the idea is that it is really very difficult to design an automated vehicle to work in every situation, every condition. The design is going to be gradual, starting from a very simple ODD, and then expanding the ODD or extending the ODD to cover many situations. So as you could see, these are conditions under which a given driving automation system is designed to function. The other term that I mentioned briefly earlier is OEDR, which is the Object and Event Detection System. So really two things here. One is the object, and the other one is the events. You need to detect them and you need to have a response to them. All of this will be useful actually when we talk about the classification of the automation levels. This is a diagram that shows hierarchically how all of these terms are combined. The DDT, again, determines the conditions under which the system works. And as you could see, the OEDR is very active here because the OEDR is about detecting objects and also detecting events. And then the R stands for response, which means that you have to do something. And the things that you can do, as you could see here, is lateral vehicle motion control and longitudinal, and also the very basic motion control of the car itself. This translates basically into steering, braking, or accelerating the car. Secondly, this diagram introduces three particular types of functions: operational functions in the inner section, the tactical functions in the middle, and then you have the strategic functions. And by the way, this document, SAE 3016, only deals with the operational and tactical, not the strategic. However, SOTIF deals with the whole thing. This diagram explains the automation levels that I talked about before. There are 6 of them altogether, including no automation. So no automation means that in the old days, maybe 30, 40, 50 years ago, where the driver did everything, of course. And then you have level 1 and 2, where the driver, as you could see, play a significant role. And then 3, 4, and 5, where the driver, the human driver, I mean, plays a less significant role. So there is a big difference between levels 1 and 2 as compared to 3, 4, and 5, okay? Because 1 and 2 is basically ADAS that we talked about, and 3, 4, and 5 are high levels of automation. So here, and very important, a lot of people get confused, especially in the middle portion. So the left one here is steering and acceleration, which means who does that? in the middle is monitoring the environment at all times, okay? And then the fallback, which means that when the automation fails, who takes over the system? Let's take a good example, for instance, at level 2 and 3, because these two are very confusing to a lot of people. For example, it is well known that Tesla is a level 2 system. And this is why if you read or know a lot about Tesla, you will see that the driver here in the middle is responsible for monitoring the environment, okay? Tesla says that in case of an accident or anything like that, the driver is responsible for everything. So Tesla is not responsible for any accidents. And the reason for that is this particular point here in the monitor. The fallback is also the driver. So the big difference between level 2 and 3, as you could see here, that in level 3, the monitoring responsibility is not the driver, but the system. So you could actually watch a movie, you know, be distracted, whatever. The system is actually doing the driving for you. Except that the ODD is a little bit restrictive. So there's going to be a situation where the system will request the driver to take over, okay? However, there is a big difference between this fallback and this monitoring, okay? In level 3, again, the driver is expected to take over, but only when the automation system fails. Whereas in level 2, the driver is monitoring the environment at all times. So it's a bit less stressful in level 3 as compared to level 2. And then level 4, as you could see, the system does the driving, the monitoring, and even the fallback. It relies on the system itself. And the only difference between levels 4 and 5 is that level 5 is totally generic. It will work in all driving modes, all conditions, whereas level 4, you may think of only some driving modes. And this is another diagram from a different context to illustrate the prior diagram that I talked about, emphasizing the role of the human on the top, basically, and even at the bottom, what the main responsibilities are. So these are different views of the same automation levels that we talked about earlier. So I'm not going to spend too much time on this one because this is a complementary information. Okay, so let's move to the actual SOTIF, and I'm going to start off with the fundamentals and then move to the standard itself, okay? So the main idea between, sorry about that, I think I went backwards. The SOTIF is that SOTIF, first of all, stands for the safety of the intended function. And sometimes there's a confusion between this standard and a prior standard also about safety, which is 26262, which is called functional safety standard, okay? And the reason for the confusion is that both standard uses the term function or functional a lot. However, the main difference is that 26262 right here, functional safety, has to do with hazards due to malfunctioning behavior of EE system. EE means electronic and electrical, by the way. Another way to explain this is that, as you know, cars today have a lot of electronics, a lot of technology, okay, that has brought in for many reasons. I'm not going to go into that, but you must accept the fact that it's a very sophisticated system and has a lot of electrical, electronic, hardware, software, sensors, you name it, right? However, these elements could fail, could malfunction. So 26262 has to do with the safety that happens whenever you have this are working fine. They are not malfunctioning. There is not failures. However, what they do is they talk about the risk or the hazards resulting to what is called functional insufficiencies. We'll talk about this term a lot. So this is the key difference. Functional insufficiencies, which is other than failures, okay? A good example of a functional insufficiency could be a performance limitation, meaning that, for instance, the perception system makes a mistake in identifying an object. For instance, it could misidentify a bridge with a vehicle in front of the ego vehicle, driving vehicle. So that is called a functional insufficiency. So nothing is failing. I mean, nothing is breaking. It's just that there are some problems related to functional insufficiencies. So the key term here is functional insufficiencies with as different or as opposed to malfunctions, which means faults in the system. Therefore, 21448, which is the SOTIF standard, really is complementary to 26262. They both deal with safety, but different aspects of safety. All right. Sorry about that. There are a few other considerations here in these slides that apply to this standard. The SOTIF standard covers ADAS as well as the highly autonomous driving, as I talked about before, which means covers all of the levels, 1 to 5. Also, this standard provides guidance to achieve the SOTIF. So it's a fairly detailed standard, except that it doesn't give you technological solutions. It's mostly from the management aspects. It gives you a complete list of methods for you to choose from. So you still need to be familiar with other aspects of the technology to implement this standard. So the standard covers several areas in the process. Covers the specification, the design, the verification, the validation, and the operation phases of a life cycle. This is a visualization of the so-called hazards that SOTIF talks about. So as you could see on the top, okay, we have several events here leading to A and then continues down the bottom on A. There are two different things here to pay attention to. One of them is the hazardous behavior, which is on the top, and then the hazardous event, which is on the bottom, and then resulting into harm or accidents or something bad that will happen to people involved in the driving environment. It could be the driver or passengers. So first of all, you have a triggering condition that will trigger a hazardous behavior, and that results in a hazard. So you have the hazard due to SOTIF type of causes that I mentioned before, functional insufficiencies. But in this case, you need a triggering condition to trigger all of that. The triggering condition works together with the scenario containing those conditions in which the hazard can lead to a harm. I will give you some examples later on because these concepts sometimes a little bit abstract. I'm talking about triggering conditions versus functional insufficiencies. Okay, but basically after this, you have a hazardous event. So the hazardous event is a very specific situation where harm could happen. And it's all related to the inability to control this hazardous event. So you have people involved here, or the driving mechanism could be automated or people that has the last say as to whether or not it will result in a harm, okay? So for instance, if you have a very good driver that will avoid an accident, then this is what we're talking about here. Or if you have a automation system that works very poorly, it will not be able to contain this event, and then that will result in an accident or harm. So this is called the hazardous event model for SOTIF, okay? As you saw, there are several blocks, several stages that will guide the activities of this standard. And some of the activities are stated here. We're talking about system specification, where we specify the function. Also, we have some design activities that are related to the so-called use cases. Think of use cases are as examples where the automation system behaves or works. And also, this will include many scenarios. As you could imagine, scenarios plays a very important role in automation, okay? And we'll talk about that. Scenarios is a very important component of the standard, and also it's a very difficult subject. These scenarios then contains these triggering conditions that I talked about earlier that could lead to harm, okay? However, an important consideration here is the situational awareness. This is where the driver may come in place and try to avoid and the event leading to a harm, to an accident, okay? So over the life, the vehicle operational life, which may take place in many years, as you know, maybe 15 years, the following can vary, can happen, okay? The environment may change, okay? And also the proper reaction could change. For instance, there are different traffic signs that are introduced, okay? So there's a lot of changes even in the operational life cycle that could take place that also needs to be taken into account. And this is a comparison between functional safety and SOTIF, okay? So the next diagram will show the SOTIF counterpart of this one, but we're talking about the sequence of events here leading to a failure, leading to a hazardous behavior, to a hazardous event, and to harm. Again, in SOTIF, as I mentioned before, it has to do with systematic faults or random hardware faults. In other words, something fails. For instance, a sensor fails, a computer fails, you know. SOTIF deals with this type of behavior as it relates to safety, you know, of the occupants. Again, the SOTIF is the complement of that. We're still talking about unintended behavior, hazardous behavior, and harm, except that the root causes are different. Now we're talking about functional insufficiencies, which is shown here as being of two types, performance related or specification related, okay? However, there is another third cause, which could be a mistake from people, and that's called a reasonable foreseeable misuse from the driver or people involved in the automation, driving automation. So again, this diagram and the prior one tries to illustrate what I said earlier as to the main differences between functional safety and SOTIF as it relates to the hazards. Now, let's move on to some terminology that's used by SOTIF standard, and they are scenario, scene, and use cases. As you could see, scene tries to depict the elements in the driving environment, which is fixed or dynamic. Fixed meaning, for instance, the infrastructure, bridges and stuff like that. Dynamics would be other cars, other vehicles, you know, people, bicycles, whatever. So the whole thing is called a scene, which is, you know, a snapshot of all of this. Now, scenario tries to model that into a time basis. So, and also including some action events, goals, and values. Okay. So the scenario is a bit more sophisticated term that includes the scene, and it depicts a sequence of events in time. Okay. Whereas the scene is a snapshot at one point in time. So that would be the main difference between the scene and scenario. And use cases include many scenarios, of course, and include additional information about how the automation system is used particularly. So you have like functional ranges, the desired behavior, the boundaries of the system. Okay, so that is called the use case. SOTIF is based on a definition of scenarios. So scenarios are classified into 4 areas. So this is a major thing about the standard. And the classification has to do with the fact that scenarios, one classification is that could be hazardous scenarios or not hazardous scenarios. Another way of classifying scenarios is in terms of whether or not they're known scenarios or unknown scenarios. And unknown scenarios are important for SOTIF because this causes a lot of problems just because they're unknown. Okay. So if you combine those 2 ways of classifying, as you could see, you end up with 4 areas called area 1, 2, 3, and 4. And of these, the most critical areas are 2 and 3 for safety. 1 and 4 are not so critical because they're not hazardous. So safety has to do with hazardous scenarios, okay? And one of the objectives of this standard is to obviously do some analysis and design and verification and all of that stuff with the goal of moving the vertical line to the left, as you could see, and the horizontal line to the bottom. And the reason for that is that what you're trying to do is minimize the hazardous areas, particularly 3. Actually, you minimize 2 and 3, but 3 is very critical only because this is something that you don't know about. Okay, this is something that, you know, a car company releases a product and they don't realize that there are some issues with the design, and only when the car is being driven, those will come up. So they're unknown. Okay. So the most critical areas again is 2 and 3. And therefore the standard actually concentrates a lot in 2 and 3, not so much in 1 and 4. Okay, let's move to the standard itself. The approach is that the standard consists of many processes and methods, okay, that are actually identified very clearly in order to do a bunch of things. Number 1 is to do what is called specification of the system and the design of the system. And all of that is in clause 5. Now, you may wonder whether or not this design is complete here, and it's not. So because this standard is iterative. In other words, we will go back and review this in several phases, okay? So clause 5 is about specification and design. Clause 6 is about the identification and evaluation of these hazards that we talked about. Okay, so this is a very important component. 7 is about functional insufficiencies and triggering conditions that I mentioned that these are critical for SOTIF. And then in 8, we talked about the necessary changes. So this is the design portion. So in 8, you make design changes to the design that you started off in clause 5 in order to address the SOTIF related risks. So this standard is very much risk oriented. Okay. I'm talking about safety risks, obviously. Now, clauses 9, 10, and 11 are pretty much related, and they deal with the evaluation of these known and unknown scenarios that I mentioned before. And then there are 2 additional clauses that are it's not explicit here, which is 12 and 13, which is basically how you finish the whole thing. It will clarify a little bit later on. So again, this is a listing of the clauses. There are 13, all of them, all together. 5 to 13 are called normative, and the other ones are informative. And most diagrams only depict the normative clauses. And here's the list. And here is a simplified top-level flow of all the activities in the standard. There are actually 3 main sections. The left side of the V, and the V here, we're talking about the V model from systems engineering, okay? That has to do with specification, requirements, design, and implementation. You know? And then the bottom which is SOTIF evaluation by V&V, which is verification validation, is the right side of the V. So the V model, and the V&V stands for verification and validation. And so here we deal with things like unit testing, integration, verification activities, and validation activities. And then, of course, the operation phase activities. This is when the vehicle is in the user hands. There could still be some issues dealing with SOTIF that they talk about. But primarily, I would say that the most important clauses are 5 through 12. This is a detail of the standard in terms of the left side of the V, okay? As you could see here, we have clauses 5, 6, 7, and 8. And this is a iteration, it's iterative. So you iterate on this portion on the left side of the V. And then right here on the bottom is the iteration on the right side of the V, meaning when you deal with testing, verification, and validation, you still iterate even going back to 8 and 5. 8 where you modify the design, and 5 is the actual design. Okay. Until, obviously, there are 2 checks here where you can exit and be finished with it. One from the left side of the V, in an iterative portion, of course, and another one from 12 where you're finished. So these are simplified diagrams. This one is a bit more involved. This is from the actual standard, okay, that puts together the whole thing that I was talking about earlier, okay? So this is a complete diagram from the standard itself. All right, the standard also has 4 annexes, A, B, C, and D. And I would say that these annexes are very, very important in that it gives you additional information and also some design methods, some more detailed examples about a bunch of stuff in the standard. So Annex A is called general guidance. And you have the A1 has to do with the argumentation for the safety case, okay? A2 has to do with general explanations and interactions between this standard and 26262, which I mentioned they're complementary. And A3, few examples, more detailed examples. As you could see, you have highway pilot, robot taxi, and a few other ones. In this webinar, I will go over very quickly the first example, the adaptive cruise control. Annex B talks about scenario. I mentioned the scenarios are very critical. So this is where they detail about scenarios and how to do the analysis based on scenarios. So there are several methods that is used for identifying misuse scenarios, for instance, or for construction of scenario factors, and the analysis method for SOTIF, adaptation of several analysis methods, and before the last one is about the use of a methodology called STPA for SOTIF. Annex C has to do with verification validation. So this is a guidance on how to do the right side of the V, if you will. Okay. So it talks about the strategy. It talks about validation targets, and also how to do the validation of particularly area 3, which is the unknown, which is a big issue for SOTIF. As you could see, it gives you additional guidance on parameterization of scenarios and sampling. All of this have to do with the fact that, in case I didn't mention that, potentially the number of scenarios in SOTIF could be millions and billions or infinite. And therefore, you need to be very careful as to what techniques and methods you use to do all of this, because it would take too much time to do the verification validation of a huge number of scenarios. So the idea is to do enough verification validation only of those scenarios that are significant for safety. Another name for that, by the way, is called safety guided verification and validation, or safety guided design. Okay. The last annex, Annex D, is a guidance on specific aspects of SOTIF, which are critical. For instance, driving policy, which means just how to drive a vehicle, basically. D2 has to do with AI, artificial intelligence, and machine learning. Okay, there are many AI techniques that's being used. D3 has to do with the use of maps, high definition maps for driving. And the last one has to do with specific communications from vehicle to X meaning that could be vehicle to vehicle, vehicle to infrastructure, vehicle to pedestrians, and stuff like that. The idea is that by using wireless communications, you could actually simplify the driving environment and the driving policy or the driving activities by using communications. All right, in the next few slides, I'm going to go over some significant sections, okay, of the standard, at least going over the main purpose of these particular clauses. We don't have time to actually go over into a lot of details of the clauses, so we'll restrict the discussion on the main objectives. So here are the objectives of clause 5, which is specification and design, which is basically, as you could see, is to collect enough information sufficient to initiate the SOTIF related activities. That's goal 1 or objective 1. The second one is that this information needs to be updated because it will change by the time you perform the other clauses. So these are the specific objectives of this particular clause. 5. 6, which has to do with the evaluation and identification and evaluation of the hazards. So this is important. Again, the main things are A here is that they need to be identified systematically. B, you need to evaluate the risk of these hazardous behaviors, because that evaluation will enable you to know whether or not you are finished for the design process. And C, as you could see, you need to define the so-called acceptance criteria of the residual risk. This is how you will know whether or not you are finished or if the risk is acceptable. Clause 7, which has to do with the identification and evaluation of the potential functional insufficiencies and triggering conditions. Again, we have two main objectives here. The A on the top is that you need to actually identify these insufficiencies of specification and performance insufficiencies leading to a hazardous behavior. So this is in the model that we talked about before. This is much easier said than done, you know, to identify all of this, because you need to have a very high level of detail in terms of the technologies that is used for this. And B, the objective B is that the response of the system shall be evaluated in terms of the SOTIF acceptability. Okay, so both of these objectives are challenging. 8 has to do with modifying your design to address SOTIF risks. So in A, as you could see here, they need to be specified, and in B, they need to be updated. And below, I have a short example of the things that you can do in this particular clause. So you can avoid measures, which means use inherently safe design techniques. You could mitigate measures for reducing the risk. You could do system modification. You could restrict the functionality of the system. You could hand over authority. That means that you may use, for instance, a supply chain so that other parties are responsible for that particular hazard. Or you could address misuses from people, from drivers and things like that. Clause 9 has to do with the definition of a strategy for verification and validation. So here is where you specify things like necessary evaluation of the potentially hazardous scenarios, coverage of the scenarios, the evidence that you need to provide for testing and verification validation, and also the procedures to generate the evidence. And the second point about this objective is that the rationale for this suitability needs to be provided. Rationale is a very thorough explanation of why you're doing things the way you're doing it. Here you have some list of methods that the standard suggests on the right side of the V. And they're in tables. And obviously there's not enough time, but I simplified here table 6, 7, 8, 9, 10, and 11, okay, which is quite long, by the way, in the context of the activities on the right side of the V. So 9, which has to do with the strategy, you have a table with techniques to do that. 10, as you could see, it's known scenarios, has the most, because they're known, we know a lot. Okay, so we know a lot about the sensors, the planning and control, the actuation, and the integration. And for each one of these, you have tables that will give you many methods for you to use. And 11 is for the unknown. Being unknown, this is quite a long list. So each one of these tables has at least maybe 10 to 15 to 20 methods. So if you add them up, you're talking about, close to 100 different methods that you need to consider. The standard doesn't force you to use all of those, but you need to analyze each one of those and determine which one is best for your design. The clause 10 has to do with known scenarios. Again, this is something that you know about. Okay, this is another diagram of that scenarios in a different perspective. Okay, so this shows the objectives of this clause in terms of the known scenarios. For instance, A says that the hazardous scenarios needs to be evaluated if they're hazardous or not, of course, to determine whether or not they're true hazards. B has to do with the functionality of the system shall behave as specified for known scenarios and for reasonable foreseeable misuse. So as you could see here, you have a detailed list of activities that all together have to do with evaluating in a very thorough fashion all of the known scenarios. The next one is the same thing, except that it's unknown scenarios. Now, this one's a bit more challenging, only because it's unknown. Okay, so there are different techniques that you use for the unknown scenarios. Okay, one of them, for instance, is random variation of parameters in simulation or in actual testing. With the idea that these random uses or parameters hopefully will lead you to unknown scenarios, because unknown, by definition, they're unknown. You run into it by doing a lot of testing in various conditions, various situations. All right, the next few slides, we talk about alignment with 26262 and also the example that I mentioned before. The stuff in gray here is the functional safety 26262 activities in that standard, and the stuff in black, which I complemented by the actual names, are the clauses that we talked about that is standard. So as you could see, the left side of the V are clauses 5, 6, 7, and 8. And as you could see here, they're aligned to various portions of the functional safety standard. For instance, item definition is totally aligned with 5, and the design is aligned with 8. And then all of that together, because it's iterative, this is the reason why it's shown like this. However, 6 is the identification of hazard. That is clearly assigned with the HARA, which the similar activity in functional safety. And likewise, 7 is totally aligned with these two portions of the functional safety standard. So as you could see, some of the alignment is more accurate, like 6 and 7, and others are not so accurate, like 5 and 8, because they are aligned with few activities in functional safety. Okay, and likewise on the right side, 10 and 11, and a little bit of 9 are aligned with these activities on the functional safety. So for this reason, a lot of people are interested in doing a integrated implementation of SOTIF and also functional safety. Let's move to the example. I chose this example, which is fairly simple, level 1. By the way, if you buy a new car, new cars today, I wouldn't say all of them, but most of them, I would say, have adaptive cruise control. Okay, so the idea is that this function enhances the standard cruise control using sensors to detect a lead vehicle. So the lead vehicle here is C2. And if the lead vehicle is getting too close, then the ego vehicle, which is C1, will take action by slowing the vehicle to match the speed of the lead vehicle automatically. Sometimes this is also called intelligent cruise control. So you need sensors to detect this distance. So here are a few examples in terms of what we talked about. The DDT is called the lateral and longitudinal vehicle motion control. Okay, whenever you are having a driver and the system as shown here. Okay, typically using a single line. So really, you're talking about detecting the lead vehicle. Okay, the OEDR is the driver, is responsible for the detection and the driving because it's a level 1 system. The fallback again is to the driver because it's a level 1. The use cases are 2. Number 1 is to maintain a headway to the lead vehicle, meaning that this question mark here is solved by maintaining a minimum distance. And sometimes that is user defined, by the way, with some conditions, of course. And the other one is that when there is no lead vehicle, the system will maintain a desired speed. Okay. So the top is whenever there is a lead vehicle, the bottom is when there is no lead vehicle. It will show you the only 2 cases of this system. In terms of the ODD, the system is operational when the vehicle is operating at or above a certain speed, So there are limitations on the lower side, and obviously, which is not shown here, also on the upper side. And here are examples of the behaviors that has to do with the behaviors for each case of the use cases. So the intended behavior is that the system will maintain a safe headway with the lead vehicle. If the lead vehicle is getting too close, the feature, that means the design, will apply the brake to maintain this safe headway. Okay. This headway will be the difference between the vehicle C1 and C2. Now, if the lead vehicle is not there or too far away, okay, then the feature will apply acceleration to go to a predefined set speed. So this is the operation of the system. In terms of the hazard that could happen here, of course, there are many. Okay, this is one example of a hazardous behavior, if you will. And this is shown in the diagram here. As you can see, the lead vehicle is going in this lane and there is a bridge in front. So what is the hazard? The hazard is that the perception system could misinterpret the bridge and incorrectly think that it is a vehicle, okay, on the roadway. And then it will apply the brakes. And this is the hazardous behavior, okay. An example of the mitigation that you need to do to avoid this hazard would be that you need to test and design the algorithms, the hardware and software. In this case, it only talks about the software algorithm. It's enhanced to differentiate between vehicles and roads infrastructures. You may think that this is easy, but obviously for human beings, this is easy. But for driving automation is very difficult. Let me just remind you, for instance, that Tesla a few years back misidentified a huge truck as glare from the sun, if you will. In other words, it didn't detect anything because it thought it was glare from the sun. And a driver who was killed drove directly into the truck that was crossing a highway, a high-speed road, actually, in Florida. This happened a few years back. So this is obvious for human beings, but the thing is that when you're talking about doing this automatically, it's not so obvious. It's extremely challenging. All right, and then to put the context of SOTIF, which is 5 here, into the so-called 7 levers of in the automotive industry that Omnex suggests to concentrate on these 7 levers, which goes all the way from IATF 16945, which is equality standards for automotive, ISO 262, which I mentioned is the functional safety standard, automotive SPICE, which deals with software for automotive, okay, software aspects. Supply chain practices means that the automotive industry works in a supply chain. You have tier 1 companies, tier 2, tier 3, and all of them need to work together. And then SOTIF, that just I mentioned now, the new standard just came out. Cybersecurity is also a fairly new standard, came out last year, okay, for security. And then in terms of design, the automotive industry uses well-known standards, which is under APQP and also PPAP, which is mentioned down here. So together, these are the 7 levers of the new, if you will, way of designing automated vehicles and electric vehicles. So this is for new designs that Omnex suggests that all companies pay attention to. Some more than others, depending upon what type of a supply chain company are you classifying. Could be OEM, tier 1 and tier 2 companies. So with that, I'm going to proceed to the summary of my seminar, of the main things that we covered. So this new standard, which was released in April of this year, it complements 21262, as I mentioned before, functional safety. This new standard addresses the so-called safety of the intended function, meaning the absence of unreasonable risk resulting from hazardous behavior related to functional insufficiencies, okay, like performance limitations. So that performance limitation I mentioned in the example is that the car could confuse the bridge with another vehicle. That's called a functional insufficiency. 21448 has 13 clauses and 4 annexes. The main features are noted here, and this is in my opinion, these are the main features. It covers automation levels 1 through 5. It defines and covers 4 areas, 1 through, there's a mistake here, it should be area 4. Sorry, 1 through 4, that's correct. The known and unknown scenarios are covered explicitly. It addresses functional insufficiencies and triggering conditions. The standard suggests, as I mentioned, over 100 methods and approaches that you could use to achieve the SOTIF. Okay. It distinguishes between 2 types of analysis, evaluations, one by analysis and one by V&V, verification and validation. So the analysis on the left side of the V model and the V&V are on the right side of the V model of systems engineering. It is aligned with 26262, and it does provide many examples of application, particularly in the annexes. Okay, so with that, that's the end of my webinar. The remaining slides is a advertisement, marketing, if you will, of additional courses. We have a complete set of courses, curriculum, if you will, in functional safety. ASPICE that I mentioned before, this is software, as well as cybersecurity. I think it was covered. I skipped that right here, cybersecurity. So those are the areas where we have a complete set of courses for you to choose from. With that, I'm going to stop and then see whether or not there's some questions in the Q&A. Okay, I have a question here that I'm going to answer. It says, in this terminology, in terms of the use cases and scenarios, so the question whether or not this terminology is consistent with the model-based systems engineering, ML or UML, and the answer is that for the most part it is. There may be some minor inconsistencies. However, that is correlated to the details. So, and the reason is that system engineering is very broad, and it is impossible for this standard to be totally compatible with systems engineering. I would say that at a very high level, it's totally compatible, but if you go into some detail level, you may find some inconsistencies, but then you have to understand the nature of the inconsistency, because they're really different subjects. In other words, model-based is systems engineering, and this topic is safety. Okay. I believe that was the only question I have. So with that, then I'd like to thank you for your attention and for joining this webinar. And if you have any questions, I believe you can send it to this particular email right here, either about this seminar or about other webinars or courses. Okay, with that, then I'd like to say thank you again, and I hope you enjoy and use this material. Okay, with that, goodbye.